recursion. So I've said that most stuff in this class isn't really difficult theoretically. It's just that you have so many of them, and it's hard to just put all of them into your head. One exception to that is recursion. A lot of students have trouble with this beyond this course. So I have students in algorithms course who still have trouble with recursion. And that's why it's very important that you have a solid foundation of recursion in this course. Have you guys done recursion in 150? Do you remember seeing it? Okay, good. How comfortable are you? Oh, you're really comfortable? Okay, that's good.
That wasn't like really comfortable.
But it was like
familiar.
okay, it was like 90 degrees. You should have this. Okay. No, I'm just kidding.
Yeah.
Okay. Right. That's fine because we're gonna start from scratch, but it's gonna be somewhat fast. So we'll do recursion basics, and by basics I mean you're gonna do recursion without helper functions or helper methods, and then Wednesday we'll do recursion with helper methods. Okay, but we're gonna start with very simple examples and build up from there. Um, so if things don't make sense, or I hope it would make sense, but it's just not natural to you. Whether it makes sense, and natural to you or not, I want you to review so that when you come here on Wednesday, everything we do today is natural to you. Otherwise, it'll be very difficult to follow the Wednesday stuff. Okay, so Wednesday we'll do very complicated, more advanced uh, recursion methods, and that it's hard will be hard to follow without having the necessary background. Okay, so let's start from scratch. Okay, so what is recursion or recursive method? In short, it calls itself within its body. And there are pros and cons to this. The code is usually cleaner. That's one benefit of recursive, probably the biggest benefit of writing something recursive. Otherwise, you would just use iterative approach. So non-recursive means iterative, which basically means using loops. Okay. So if the recursive version is not simple enough, you might as well just go with loops, right? And that's probably the reason why pretty much all recursive methods you see be very clean, very short. And when you get to the lab this Friday, you'll see that like all the recursive methods I have to write are short, but it just takes time to come up with that, right? So that's the advantage. You have very simple code. Disadvantage is that it's typically slower because every time you make a call, Java allocates memory for that call, for local variables, parameters, and so on. So when a recursive method keeps on calling itself, say it called itself 5 times, then this allocation of memory happens 5 times, and each time it takes time. So that's why it's usually slow, and for the same reason, it usually takes up more memory than iterative approaches. And you may think that's severe enough that you wouldn't want to use recursion, but there are cases where it's so much cleaner to do recursion. So people still do use recursion, though not as often as they use iterative solutions. Okay, so that's a bit of background. Well, another disadvantage is often harder to understand, but sooner or later that will be less of a disadvantage for you once you get used to this. Okay, let's think about our first example, which is factorial. What is a factorial conceptually? Let's say n factorial. Net.
Well, it's just 1 times, 2 times, 3 times like that.
Up to Okay, good. And let's say that in reverse. So n factorial is n times n minus 1 times so on until you get to 1. Okay. How would you write a method that computes factorial? So let me just write out the header for the method. So public static int fact int n. And this should return n factorial. How would you implement this? You sure?
As we learn n times fact n minus 1.
Okay. Uh, you're ahead of my plan. Now, let's say we haven't done recursion yet. I'll get back to you. Brandon?
If we haven't done the first yet, we probably like four, you actually do wall n is what you make a new variable, wall n is greater than one, your new variable, which we started one, just have a baseline for one time, then multiply by n, decrease n by one,
Right.
multiply by n, decrease by one, until it gets down to one. Thanks.
Yeah, so that's good, except you want to use for loop. Anytime you know how many times the loop should repeat.
One.
Okay. So you want to start by declaring a local variable that is to store the product. Say result. My pen works. You sure? Have you learned recursion?
Yeah.
In your high school? Okay. Okay. It's good. In CS, no, like in what course?
There's the recursion was in the curriculum in high school.
But like what course? Math?
It's not.
Math? Okay. Okay, that's good. Okay. So this is a product I'm going to return at the end. And I'm just going to have a for loop that repeats n times. So I'm going to set I to n while I is greater than 0, I minus minus. And I just multiply I to result. And then once the loop is over, I've multiplied all n numbers. So I'm just going to return that. Okay. So this is probably what you're used to. This is a iterative approach of solving this. Brandon?
It would actually slightly more efficient go to I is greater than one, you don't for one, instance for one, it's not a bit thing.
Yeah, you could do that. Either works. So it depends on how you think of this as. Are you thinking of that as the last digit, or are you thinking of that as a multiplicand that doesn't affect the product? Okay, so that's our iterative approach. Do you remember yourself not being able to do this at one point? You've made a big progress. Okay, now let's think about the recursive solution. So for this, let's first define what factorial is recursively. We defined it as n factorial is n times n minus 1 and so on and so forth. That's actually an iterative definition of factorial. To define it recursively, I can say, well, n factorial is just n times n minus 1 factorial. That's a recursive definition. But I still have to say, where does it end? Then I'll say, well, 0 factorial is 1. So that's a recursive way to define what a factorial is. N factorial is just n times n minus 1 factorial, and 0 factorial is 1. Do you see how that's the same thing as defining n factorial as n times n minus 1 and so on? Okay, good. Now, let's look at this. Literally, the factorial sign is a method. Okay, so we need a method, let's call it fact, where if you pass in n, it should return n times factorial of n minus 1. The same method, fact, if you pass in 0, it should return 1. That's literally translating our recursive definition into behavior in terms of, I mean, semi-Java-ish, right? Okay, and now let's write up the actual method. Public static int fact int n. Notice that this is exactly the same as that. From the user's perspective, I should not know whether it's done recursively or iteratively, as long as it returns the right return value. Okay, how do we write code that behaves differently depending on some condition? Angel? If statement, good. And what's the condition we're checking for? Great. So if n is 0, that's the first case, then I'm going to return n times factorial of n minus 1. Or if it's 0, it's the second case. You return 1. If I can spell return correctly. Otherwise, you return n times factorial or fact of n minus 1. Okay, Brandon? Yeah, we're going to assume that the input's positive. Yeah, you run into the same issue in the iterative approach if you put a negative number. Okay. Any questions about how the recursive version is implemented? Okay, so we just have two different cases. If n is 0, return 1. Otherwise, you have to return n times factorial of n minus 1. Let's see another example. Actually, before that, let's see what happens. So this is called recursion tree. We're going to trace the calls and return values. Okay, so let's say we wanted to figure out what factorial of 3 is. And we just call this fact method and pass in 3. Okay. If it were a iterative method, it will just return 6 and we are done. But in a recursive method, that's not what happens. Since n is not 0, it's going to try to return n times factorial of n minus 1. But to execute this line, this call has to finish first. So Java actually makes another call to fact. Now this time it passes in 2. Same situation, 2 times fact of 1. To compute that, you have to wait to figure out what fact 1 is. And the same thing happens here. Now, think about this call. Fact is called and n is 0, in which case I don't have to wait for anything. I can just return 1 right away. So this thing will return 1. Okay. Now think about what happened here. Fact 1. We're waiting at this line. We knew n is 1. We're waiting for this value, which now we know is 1. So you multiply that to 1 and return that value. Okay. What happened here? Well, we're waiting down here 2 times fact of 1. Now we got the fact of 1 return value. So you multiply that to 2. Okay. And then same thing happens. So 6 is returned. Do you see this? Okay, good. You should be able to do this yourself for more complicated recursive relations. So again, this is 1 times fact of 0. This is 2 times fact of 1. That's 3 times fact of 2. Okay. And let's say we have called this from the main method. Okay. Let's look at a different example. Fibonacci numbers. Does anyone know what Fibonacci numbers are? Ned?
Well, it's like it's like a sequence, so like you add a number, I think you like start with 1, and then you add the difference to the 2 previous numbers onto it's kind of hard to explain, but like the next number, so like it would go like 1, 2, and then 5, because
Right.
yeah, it's, I don't even remember it myself.
No. Yeah, if I had a transcript of what you just said, I'll delete some words and it will be a correct description of Fibonacci numbers. Yeah. So it's a sequence of numbers where you start with 2 ones, and then nth number is the sum of the one before and the one before that. So nth number is the sum of n minus 1 plus n minus 2. Okay, so what would be the number that comes after this? Angel?
Did it create a triangle?
Triangle? No, it's a sequence.
Oh,
Yeah. 2, and then the next one would be 3 because it's 2 plus 1. The one after that would be 5 because it's 2 plus 3, 8, 13, and so on. Okay. And let's give them the indices. 0, 1, 2, 3, 4, 5, 6, 7, and so on. Okay. So let's say the 0th Fibonacci number is 1. The first Fibonacci number is also 1. Second Fibonacci number is 2, and so on. Okay. Does the sequence make sense? Now we're gonna create or write a method that returns nth Fibonacci number. And let's see how it should behave. So this 5th method we're writing, when you pass an n, what should it return? Like a general case n. Lena? Okay, good. But I said general case. But let's write that up since that's correct. Okay, if it's 0, 1, what if it's 1? Also 1. What if it's n? What should it return? If you pass in n, what should it return?
Like n minus 1 plus n minus 2.
Very close. But we don't want to add n minus 1 and n minus 2. We want to add n minus 1th Fibonacci number and n minus 2, and my second Fibonacci number. So what change should we make to that? Fib of, yeah? So fib of n is fib of n minus 1 plus fib of n minus 2. Right? I mean, we're thinking of fib as a method, which it is. But if you just think of it as fib of n as nth Fibonacci number, then I'm asking what's nth Fibonacci number? Then you would tell me, well, that's n minus 1th Fibonacci number plus n minus 2th Fibonacci number. Now that we know how the method should behave, we can do the same exercise where, okay, we have one method called fib. It behaves differently depending on the input, right? If you pass in n, it should return fib n minus 1 plus fib of n minus 2. If you pass in 1, it should return 1. If you pass in 0, it should return 1. Okay, so we have a method that is supposed to behave in 3 different ways depending on what the input is. And you can arguably merge the last 2 cases into one because they have the same return value. Okay. So let's write this up. So we have public, static, int, fib, int n. What are the conditions we're looking for? Kathleen?
And 1, 0, and 1.
Good. If n is 0 or n is 1, then return 1. Otherwise, return fib of n minus 1 plus fib of n minus 2. Okay. Questions? Angel?
It's just a small thing,
Mhm.
like on a test when we're writing code,
Yeah.
you have the braces for the function, do we need it for the if statements?
Okay. We need braces for if statements. This if statement. Why not? Why don't we need braces for this if statement? You told?
Since there's only one line. but-
Yes. So for if statements, loops, if there's only one line in the body, you don't put braces, or you could put braces, but let me put it the other way around. If you don't have braces, Java will take the next line as the only line in the body. So whenever you have if statement or loop with one line of code, you could omit the braces. Okay. Any other questions? Okay, good. Can you visualize what the recursion tree will look like? Ned?
Well, like, it creates like two new instances of the method for the call
Right.
for every time you call it, so it's gonna like be like a branching tree is
Mhm.
two for each.
Yes. And I guess I just use the word recursion tree. So it splits into multiple paths. So same as before, let's say I wanted to figure out what Fibonacci, the third Fibonacci number is. So I called fib3 from main methods, for example. We'll get to this line and say, well, or Java knows that it needs to return this number, and to return this value, it first has to know what fib and -1 is. So it calls fib2, and note that from fib3's perspective, as usual, it goes left to right, which means until this finishes, this is not called. So it's not like you're calling both and then get them both at the same time. You actually go from left to right. So you don't even call this until this thing finishes. Okay, so you first call fib2, which itself is a call to fib. Okay, we'll have to figure out fib1. Okay, fib1 is actually this case where we don't have to wait for more values. So we'll just return 1 right away. From fib2's perspective, you just got this value. Okay, now you know this is 1. And then you have to figure this out before you can decide what to return. So it would call fib2 minus 1, which is 1. Or 2 minus 2, which is 0. Fib0 is this case, returns 1 right away. Now, from the perspective of fib2, we just figured out 1 plus 1. Or we got value 1, we got value 1. Now we can add them and return. Return 1 plus 1, which is 2. From the initial call to fib3, or the initial call to fib, where we pass in 3, we just finished this and we figured out, okay, this is 2. Now we have to get this value. 3 minus 2 is 1. So fib1. Okay, and fib1 is this case, so it returns 1 right away. From the initial call's perspective, we just got this value returned. We just got this returned as well. So now we're ready to add them and return. Okay, so again, this is factorial of 2 plus factorial of 1. This is factorial of 1 plus factorial of 0. Okay. Any questions? Ito? What did I say? Fact. Right. Thank you. You passed my test. Just kidding. Any other questions? Ned?
When is this like practical? Because I'm looking at it and it seems like it's a really like inefficient in terms of like
Yes.
so you do like a really high number. Isn't it like 2 to the n or
Yeah, so it is extremely inefficient. I mean, even from this picture, you can see that fib1 was called multiple times. Imagine the initial call being like fib10, right? So it is inefficient in this case. It's especially inefficient in this example because the same call is made multiple times. But when you do use Fibonacci, or when you do use recursion, you typically use it in cases where you don't have a recursion tree that looks like this. And there's a trick called memoization where it's off topic, but you'll run into it. So it's something good to learn. There's something called memoization where for whatever method you memorize, it keeps track of input and output pairs. So when field one is called for the first time, because you have not seen it before, Java will go through all the process and then keep track of input and output. When it sees the same call with the same input, it looks up the table and returns a value right away. So you can actually prevent Java from repeating the recursive calls when it's called this for the second time and so on. But anyways, yeah, so you're correct that it's quite inefficient in this case. But there are cases where you don't have this much of inefficiency, and you'll soon see. Any other questions? Okay, so now you're seeing this and saying, okay, this makes sense, but when you come back here on Wednesday, you should be at a point where trying this out is very natural to you. Because we'll do something much more complicated. Okay, now we've seen two examples of recursive methods. We're gonna talk about the general structure of recursion. Every recursive method has two cases, or two types of cases. One is base case, and the other is recursive case. And base case is basically the case where you stop recursing. So if you think about factorial, the base case is if n is 0, return 1. And then recursive case is obviously the case where you recurse. So for factorial, it's where you return n times fact of n minus 1. Okay. Do you agree that every recursive method has a recursive case? Or one or more recursive cases? Yes, obviously. Otherwise, it won't be a recursive method. So you know this is there for sure. Would every recursive method have a base case? Or one or more base cases? Why? How can you be sure? Lena?
So,
Yeah. If there's no base case, it'll be infinite recursion. So you know you have both, and I like to have a very clear distinction between the base cases and the recursive cases. Like when you have multiple of these and multiple of these in the same method, it's sometimes possible to have them intermixed. But I like to keep all the base cases at the top, all the recursive cases at the bottom. So it's very clear when does it stop and how does it recurse. So you'll see me always commenting base case and then recursive case. In fact, that's how I start. Before I write the first line of code, I would start by commenting to remind myself that I need to have both of these. Okay. Your first example. Ned might ask me, like, why are we doing this? But this is the simplest recursion that I could think of. So it's called count horse legs. It takes in the number of horses and then returns the number of legs. Okay. So if input is 1, it should return 4. If the input is 8, it should return 32. Okay. So suppose there are 6 horses. So the input was 6. So I'm trying to present you a different idea of what recursion is. Because if we say recursion just means you call itself, it could be very abstract. Well, I guess what I'm trying to do is also abstract, but I'm trying to give you a different perspective just in case that doesn't seem natural to you. So another way to look at recursion is this. Suppose I'm given the task of counting the number of legs of horses, 6 of them. And so that's me. A student drew me in the final evaluation back when it was pen and paper, like 1970s. Just kidding. I wasn't even alive. Okay, anyways. So me being lazy and smart and having the ability to create a clone, I say, well, I'm not gonna go through all the horses and count the legs myself. What I'm gonna do is I'm gonna count the number of legs for the horse I'm looking at right now, and then have my clone deal with the rest. Okay, I'm gonna tell my clone to count the number of legs for all the other horses. Once that clone tells me the number, I can just add 4 to that, then I'm done. The clone, who's a clone, who's also smart and lazy, thinks, okay, I'm gonna count the number of legs for this horse. The remainder, I'm gonna have my clone count. And this process continues until you get to a clone that who doesn't have any horses to count the legs for. Okay, so then from this guy's perspective, well, I don't need a clone. I just tell my boss, so to speak, that there are no legs. Okay, so he says, okay, there are no legs. From this guy's perspective, okay, I see 4 legs, and then my clone says there are no more. So he tells his boss, okay, there are a total of 4 plus 0 legs. What would this guy say to this boss? Angel? Yeah. I see 4, and my clone says there are 4 other legs. This guy. I see 4, and my clone says there are 8 more. 4, 12 more. 4, 16 more. 4, 20 more. So total of 24 is returned. Okay. Now think of each of these as a method call. Okay. That method behaves in 2 different ways. Sometimes it just returns 0. Other times it returns 4 plus whatever the recursive call returned. Those are the 2 cases. Okay. So I want you to take time to write this up. And I guess I'll show you the other slide. But thing to keep in mind is there are 2 different behaviors of this method. It's going to be very short. In fact, 1 line for the first case, 1 line for the second case. Thirty more seconds. Okay, good. So what's the condition? What's the condition for the if statement? 이통? Let's say again.
The gains non forces equals zero.
Yes, if num horses. Okay, so base case. Recursive case. If num horses is 0, return 0. Otherwise, you return 4 plus count horse legs num horses minus 1. Okay. Did anyone stop the recursion one step earlier? Angel?
Well, I mean, my conditional statement was different, it does the same thing. It was if num horses is less than 1.
Okay, yeah. Yeah, that works. You could have done, if it's 1, return 4. That's stopping the recursion here. And we'll see more of this. But basically, in this case, the code doesn't get any more complicated. But in most cases, if you stop the recursion earlier, let's say if there are 2 different recursive cases, and if you stop the recursion one step earlier, then you would have to have 2 cases within base case. So the code gets more complicated. So generally, you go as far as you can without stopping the recursion early. Because like if I say, you could stop when the number of courses is 1 and return 4. You could also say, well, I can stop when it's 2 and then return 8, right? But the downside of that is now it cannot deal with case 1, right? If the recursion starts wherever and then stops at 2, then it doesn't know how to deal with 1. So for the same reasoning, if I change that to 1, now it cannot deal with input 0, right? So that's another reason why you would go all the way down to 0 instead of stopping early. Okay. Any questions? Good. Now, slightly different example. It's called contains. It takes a string and a char and returns true if that string contains the char. So for example, if the input string is AACBDA, same thing happens. So I'm in charge of this, but I'm not going to check all the letters. I'm only going to check the current letter. And if there's no match, I'm going to have my clone check the rest. Okay. And then the clone thinks the same way. I'm just going to check the current letter. If it's not the letter I'm looking for, I'm going to have my clone check the remainder, and so on and so forth. So let's say our input or our arguments are A, A, C, B, D, A, and then say we're looking for a Z. Okay. All the way down. There's no more letter to check. So obviously you don't see a match. You don't see a Z. It says false. Okay. Well, with this return, well, I don't see a Z, and my clone says there's no Z beyond this point. So returns false. And same idea. Returns false all the way. Okay. What if the input is something that's actually in the string, say C? What would it look like? When you get to this point, this clone will say, well, I do see a C. So it returns true right away without making a recursive call. From this guy's perspective, I don't see a C, but my clone says there's C beyond this point, so returns true. Then returns true. Do you see the difference? So we talked about how it ends, how the recursion ends. So these two must be two different base cases. So here's your first base case. And then here's your second base case. Okay, so your method should have two base cases. In the first case, it returns false. Other case returns true. Now, can you tell me what the condition for this base case is? Like, at this point, why did we stop recursing? Connor?
The letter on the STRs, the X.
Yes, good. So this is a case where we stop recursing because we found what we're looking for. Here, why did we stop recursing? Captain?
Because we don't.
Yeah, we have no more letters to check. So those are the two base cases you want to have in your method. For this method, we'll have to use some methods from the string class. There are a couple different methods. So you have there's a char at method. Returns a character at index I. So if you go str.char at 0, it'll return A. And then there's a substring method. Okay. There are different versions, but the version we're going to use takes in one index and returns string starting at that index. So if you do str.substring 2, 0, 1, 2, then it will return the string CBDA. Okay. And then lastly, the length method, which returns the length of the string. So if you do str.length, it will return 6. Okay. So please implement this method. Just remember there are two base cases. And then think about what the recursion does, what the recursive case should do. Yes.
The substring, that's another argument. Like the next one would have to be three.
Yes, but that is not going to be what we need for this method. Yes. I'll give you about a minute. Let me know if you have any questions. 30 more seconds. Okay. Let's do this. So as usual, I'm going to start by commenting base cases and then recursive. Okay. So what is the first base case and how do you check for that? How do you check if it's the first base case? Ned?
Well, I mean, it depends on how you like do the string, but if you say like the string is like equal to like, I guess it would just be like null or whatever makes the string like equal nothing, then you return false.
Right. So this empty string is not the same as null. Right? If you think about what's inside the string, the string variable, the str variable. In the case of null, you don't have any memory address, it's just null. In the case of empty string, it will have the address of wherever that empty string is. Say address 88 or something. Yes? Do you see how they're different?
Yeah.
So in this case, what are you looking for?
Just an empty string.
Okay. So how do you check if the string is empty? Ned?
If str is equal to just quotation marks.
Right. Okay. So there are several ways to do this. The one I intended is using length. str.length is 0. You could also use is empty. str.is empty. If you want to compare it against the string, open and close double quotes, then technically you should do str.equals double quotes. Now, because of the details of implementation, or because of the optimization Java does, you could actually do str equals double empty double quotation marks. It will still work. But let's use length because technically you can only use those. Okay. So the first base case is we're checking whether a string has length 0. If str.length is 0, then you return false. How do you check for the second base case? Connor?
str char dot equals x turn true.
Good. So the way we're using substring, we're chopping off the first letter, which means you want to check that first letter before you chop it off. Right? So we're always going to check the first letter. If string dot char at 0 is what we're looking for, then return true. Otherwise, the recursive case, which is you just return whatever was returned in the recursive call. Return contains the same string, but with the first letter chopped off. So str substring. One, and then same target char. Okay. Any questions? Okay. We'll do a slightly more advanced version. So this time, instead of returning Boolean, we're going to return the count, the number of times X appears in the string. So same example. Now, say if we're looking for C, so we don't stop early this time. So there's no base case 2 that stops early. We still have to go all the way to the end because we're in the end we want the actual count. This thing returns 0. I don't see any. So 0 plus my clone says no more. So 0 plus 0. Zero plus 0. 0 plus 0. Now here, I see 1. So it's 1 plus, my clone says there's no more. So it's 1 plus 0. What would this guy return? Well,
0 plus
0 plus 1. I don't see anything. 0 plus my clone says there's one more down the road. So 0 plus 1. Good. Okay. What if you look for something that appears more often? Say A. 0. 1 plus 0 because you see a 1. 0 plus 1. 0 plus 1. 0 plus 1. 1 plus 1. Ugh. 1 plus 2. So we only have one base case. So we only end when we run out of characters to check. But now we have two different recursive cases. One case, you add 1 to the return value. In another case, you add 0 to the return value of the recursive call. Recursive convert. Okay. Okay. So I'll upload the slides with the code for this, but the idea is we have a situation where there's only one base case, but two recursive cases. One, you add 1 to the return value of the recursive call. 2, you add 0 to the return value of the recursive call. Okay. But you'll see the code for that. Thank you, and I'll see you on Wednesday. Thank you.